All right. Now, what do we need in the data center networks? First thing we need is they need to be scalable. Means we need to be able to add more and more and more as we need it. Secure. Obviously, you don't want not only outsiders getting in, but also insiders getting to other people's network. For example, if you have a finance department and a marketing department, you don't want marketing people to see the finance data or finance people to see marketing data. Shared, while they have to be able to use the same servers and same networks, the two departments. Standardized, and you don't want to be logged into a particular vendor or one company. And simplified, and you don't want a network which needs lots of experts, so it's simple to manage, right? And so they call it 5 S's: scalable, secure, shared, standardized, and simplified. Now, second thing is converged infrastructure. In the old days, the servers used to use one network and storage used to use another network. And we will talk about that in the lecture after next, actually, what network apps they use. Just for those of you who already know, storage companies or storage devices use SCSI and fiber channel and things like that. Right? When you connect in storage, you don't connect to Ethernet generally, you connect it to SATA, ATA, things like that, right? Fiber channel. Those are different kinds of networks than Ethernet. And that was a problem. So now we want to really need one network for both, servers and storage. And we want the network to work with both of them. Workload mobility. We need even larger number of servers in a domain. So we need very large domains for virtual machines. Previously, we used to have physical servers. Now, each physical server now has 10 virtual machines, or maybe 8 cores, 16 cores, and so on and so forth. And so the number of processors is going up, and the number of nodes is going up, and so we need large domains. East-west traffic. In the old days, the traffic was going up and down to the customer, back, customer and back. Now it is going sideways, right, from one server to the next server. So the old networks were not designed for that kind of traffic. So we need to worry about that. For example, Facebook author gave the statistics that your one Facebook request requires 88 cache lookups, 35 database lookups, 392 back RPC calls, and so this is all inside the data center. Okay, you just made one request inside, and so many hundreds of requests went inside, east-west, right? And so the internet traffic times 935. So basically, I think the word here should say intranet traffic, not internet. So the inside the data center traffic was 900 times what went out. If you added the request and response, HTTP request and response, 935 times that went inside the network, intranet. And the storage traffic on the Ethernet also causes problem because storage doesn't like loss. If you read a disk and it turns out that there is no data, you are going to be in big trouble. Right? And while on Ethernet, you do it all the time, you lose packets and frames. So Ethernet, if it wants to serve the storage, it has to change. So those are the requirements. And there are more which will come up as we see, but these are the 5 top ones. So 4-post architecture at Facebook. So now the one that I showed you before, though that is not the only one kind of architecture, and the big companies are always discovering better things. So Facebook has this architecture which is slightly different than what we saw before. So let's see what it is. It's a 4-post architecture, they call it. And in a minute it will become clear what is a post. So they have these rack switches. They have 10 gigabit links going up to cluster switches. You see, each rack switch is connected to each of the 4 cluster switches. The cluster switches are connected by 4 40 gig uplinks to each of the 4 fat cats, FCs, fat cats. These are real big switches. All right, 40 gig. 4. So it's not by 2, it's by 4. So now you see fat cat aggregation switches. So these are the aggregation switches for them, and these are access switches in their terminology. So the terminology already changed. All right. So now there is a 4-to-1 oversubscription. Now there is one more thing. These red lines. These cluster switches are connected in a protection ring. What is a protection ring? Protection ring idea came from the telephone companies. So all the telephone networks have a ring-shaped network. And so let's say these are the 4 switches. They will be connected like a ring here which goes clockwise and another ring which goes counterclockwise. These are directional in the sense that this could be fiber which is light is going like this. This could be fiber in which light is going like that. Okay? If something fails, let's say this switch fails, then this switch will realize that this has failed. It will just short circuit this link here. This will realize that it has failed, and now there is a ring which is working. At least the 3 switches are talking to each other. So this is called a protection ring. Okay, and this is very common in the carrier industry. So Facebook uses that. So this one, 4 switches are connected in a 10G by 8 protection ring. So there are 8 fibers going. And the 4 FCs are connected in a 10G by 16 protection rings. There are 16 rings here. Now, there are no routers so far, you see. Everything is switches. That is one good thing about this, is that anything can move anywhere here. Second thing is, one CSW failure reduces intra-cluster capacity to 75%. So let's say this switch failed and 3/4 is still up. Right? So that is 75% right there. Is this a dual protection ring or single protection ring? I would tend to call it dual. So that means there are total 2 fibers in it, and it is a dual. So it will have 8 fibers, but it could be they have 16 fibers. So I mean, I don't know that part. So, but anyway, there are 8 protection rings, which generally I would think means that you could have up to 7 failures, and something will still go through. Okay, so this is highly protected 16 times, and this is the so on and so forth. So now here, 4 CSWs are connected. One CSW failure will reduce by 75%. By the way, all of this is in this paper which is already referred, so you can also read that and see what if it has any sense in it. But the idea is that if you just do 2 at a time, then one switch goes, the capacity goes by 50%. Right? Which is not good. So here they have 4, so the capacity goes down by 75%. The capacity goes down by 25%. All right, now you could increase these numbers and put bigger rings, but then there is a trade-off. If you have bigger rings, there are more failures, and the rings will fail more often. So you don't want to put too many in that either. Now, this is a hot research topic, how to arrange the data center networks. And I did not want to go into the research part of this. I just wanted to keep it because there are so many research papers on this. Actually, I made a list, but then I didn't put it here. And so this is a current research topic. And every time you go to SIGCOMM, which is the leading conference, you will find 1 or 2 papers on this topic itself. But here is the idea. The latest idea was, or not latest, one of the ideas was that we use class network. And the class network are named after Charles Class, 1953. He worked for AT&T and came up with this idea. Basically, in those days, all the switches were real switches, something you turn on and off, cross point switches, right? And so he designed a network which will require the minimum number of cross points. So if you want to do something, you use his network. And so here is the idea. So if you have a 3-stage class network, actually more like class network, is that you call it R, N, and M. You have to, if you have 3 stages, you call it clause R, comma, N, comma, M. And in this example, I have taken R equal to 2, N is equal to 4, and M equal to 3. So you have R, N by M switches. All right. So in this case, 2 4 by 3 switches. 4 in, 3 out. In the first stage. The second stage has M R by R switches. So there are 3 2 by 2 switches. 2 in, 2 out. And at the end, you have just the opposite of the input. So you have 3 by 4, 2 of them. So you have 8 in this case, and 8 out. So this is 8 by 8 switch. And you can calculate how many cross points are there. This one has N by M cross point, this one has R squared, and this one has M by N cross points. Okay? You can add them up, and then you can find out what is the optimal value of R, M, N, and so on and so forth. Everybody understand that? This is a homework actually, so you need to understand this very well. Okay? Now, notice that this is all one-dimensional. One directional. Everything comes in and gets out, right? So when this networking people wanted to use this now in today's network, we don't have anything much one dimensional. Everything is bidirectional. You send it and you get it back. Although inside the wire you generally send in one direction. For example, in the copper you send it in this direction, and then another copper wire goes in that direction, or fiber, and so on and so forth. But generally both input and output are at the same point. Right? So what they did was they folded it up. You draw it on a piece of paper and draw a line in the middle here and then fold it. Okay? You will get this network. Everybody sees how to get from there to here? You draw a line in the middle and fold it. So everything becomes bidirectional. Alright? Now, in our traditional sense, we will call it a 4 by 3 switch because it has we will call it a 7-port switch. Not 4 by 3. This is a 7-port switch because when you buy a switch, it doesn't say this is input, this is output. Everything is input, everything is output. Right? So you have a 7-port switch, and these are 2-port switches. So this is a folded clause. This is also called a fat tree because the person who first invented it designed a tree. And by the way, this doesn't have to be just 3-stage. You can draw a 3-stage clause or 5-stage clause or 7-stage clause or 11-stage clause, and bigger and bigger, bigger and bigger. When you fold it, you get a real tree, nice tree. All right? And the capacity, basically is higher and higher toward the root. So that's why it's called fat tree. Fat tree is very thick at the base, and then as the branches come out, they are thinner and thinner and thinner. So that's the fat tree topology. So here is a fat tree example. There are 6 switches which are identical. All these 6 switches are identical. All of them are 36-port switches. And all of them are 1 gigabit ports. And so what we do is we connect 72 servers like this. We take 18 servers and connect to 18 ports on this switch, 18 servers to this switch, 18, 18, 18. So there are 72 ports which are used up on this side for 72 servers. Then we take the other 18 ports, we give 9 links straight to the 9 of these, another 9 to 9 of these, okay, on the right side. And similarly for the other ones. So now you see 9 plus 9, 18 plus 18, total 36 ports have been used up here, 36 have been used up here, 36 on every switch have been used up. Everybody understands how do we get these thick lines? There are 9 cables going in the same place. You put in the 9 different ports. So this is a fat tree network because you can see the capacity here is fatter. Alright, now the interesting thing about this network is The throughput between any two servers is 1 gigabit. If you use equal cost multipath, A can talk to this one at 1 gigabit, B can talk simultaneously to this one at 1 gigabit, and C can talk to this one at same. They will not trample on each other. Everybody has 1 gigabit and everybody can use 1 gigabit to talk to anybody else. Obviously, if everybody wanted to talk to me and everybody has 1 gigabit, you will have trouble because I am the bottleneck. But switches are not the bottleneck. So this one is what they call full bisection bandwidth. Bisection means you cut it any way you want and you get the full capacity. So basically, so this is identical bandwidth at any bisection and you get 1 gigabit. And so this is very good topology. The main problem is though that you used lot of cabling. This is, as you can see right now, you are using basically the cabling complexity goes up very fast on this one. Okay, so if you put money on the cable, then you get full bandwidth. All right, that brings us to the end of this chapter. 5 key messages. First is that remember those modular data centers that can be sent, basically a truck kind of thing. You can use it for easy assembly and scaling. So you don't have to start with the racks and start filling them up. You can get all the racks and everything else together. Second thing you learned is that there are 3 tiers: access, aggregation, and core. If you wanted to add, then you would know that the access and aggregation are layer 2, aggregation and core is layer 3. Right? Application delivery controller go between the aggregation and the core in the layer 3. And you need large L2 domains. Why you like L2 domains? Because you can move anywhere without any rework. Moving between L3 domain requires a lot more work, so you need large L2 domains. And then there are many topologies. Fat tree topology is used to improve the performance and reliability. Homework 3. Draw a 3-stage clause 4-5-3 topology. Alright? And its folded version. Then fold it and show us the folded version. Acronyms are there, all of them, but then there is a reading list, which actually is the same as it was in the slides. I just collected all of them and put them at the end. So you can click them. As I said, these are all clickable. You can download the single slide version from the website and then you can click on it and you can read them, and you must read them. And then I also did was Wikipedia separately. So these may not be in the main slide set, but if you read these parts of the Wikipedia, you will get all about some of these things. For example, even the clause net.